Hey everyone, welcome to the fourth video of the NIA Basics batch, part of OWS Education, created by the OWS team. In this video, we will look into how NIA's sharding mechanism works and how it allows the NIA network to be scalable and secure. So let's dive in. Now that we know from our previous video how NIA uses TPOS to select a set of nodes to validate transactions, let's look into how the validator nodes actually compute transactions and how they come to an agreement for the state of the NIA blockchain. In proof of stake without sharding, all validators must process every single transaction sequentially to agree on the state of the blockchain. This is what we call its global state. This limits the throughput of how many transactions can be processed per second, known as the transactions per second or TPS of a blockchain. On the other hand, in proof of stake with sharding, validators only need to process a subset of transactions to agree on the global state. This allows the throughput of transactions to be increased considerably, up to 100,000 TPS for NIA. But how can validators of the NIA network only process a subset of transactions and still come to a consensus about the global state of the NIA blockchain? To answer this question, let's begin with two basic points. The first is that the NIA blockchain can be thought of as a line of horizontal blocks, sequentially tied by their headers, like any typical blockchain, where its global state is the state of the most recent block. Secondly, for NIA, each block is composed of chunks, which are just different bundles of transactions found in each block. So, what processes the transactions in each chunk? Shards. NIA uses a mechanism called Nightshade to organize how shards process transactions found in chunks and how the shards handle cross-shard communication. If we imagine blocks running horizontally and tied sequentially to the previous block, then shards also run horizontally and are tied sequentially to their corresponding shard from the previous block. This makes them like little chains within the main chain. Each shard only processes its line of chunks for every block, communicating to other shards only if cross-shard transactions arise. The NIA blockchain is capable of being split into 1,000 shards, but uses dynamic resharding to use only what is needed according to on-chain demand. Because every shard only processes the transactions found in its chunk, chunks from different shards are processed in parallel to each other, increasing throughput, or TPS. This also means that each shard has its own local state. So, if each shard has its own local state, what does the processing in each shard and how can the local states of shards unify into a global state for the NIA blockchain? Well, validator nodes selected by the TPOS algorithms are responsible for processing these shards. The TPOS algorithm assigns validators at least one shard. Validators then process their chunks into local shard states. The TPOS algorithm then assigns block validators the responsibility of computing the global state of the NIA blockchain based on the local state of each shard part of the network that they receive from the shard validators, and creating a block from the computation. NIA uses a mechanism called Doomslug to allow block validators to firstly gather shard states, secondly compute, thirdly produce, and lastly broadcast a block in under 2 seconds. The process commonly referred to as finality. So, we have now built up a description of NIA's sharding. Validator nodes are assigned shards. Each validator then processes all of the transactions found in the chunk of their shard, resulting in a local shard state. The network then takes all of the shard states and computes a global state. Finally, what does this mean for the blockchain trilemma? About scalability, the combination of a potential TPS of 100,000 and a finality of under 2 seconds renders the NIA network highly scalable. And about security, the probability that a single shard takes over decreases exponentially to the number of validators in a single shard. Additionally, Nightshade solves two known issues with sharded blockchains. The first is secure state validity and the second is data availability. State validity ensures that shard states are valid even when the history of that shard is unknown, while data availability ensures that data communicated across shards is valid and available. How Nightshade solves these two issues will not be explained due to its complexity, but feel free to check out NIA's official document below for a description of it. In this video, we explained how NIA's Nightshade allows validator nodes selected by the TPOS algorithm to process and validate transactions securely and at scale. This also gave an answer to how NIA has handled the blockchain trilemma. In the next video, we will explain how you can interact with the NIA blockchain using the easy-to-use NIA wallet. Thank you, and see you next video.